In section 3 of chapter 6, we're going to take a look at rational numbers and decimal representation. Now, as we look at these, they look like fractions, but notice that the 9 is over 1. Every number that doesn't have a number under it is over 1. Now, there are different ways to represent this 9 over 1. It could be 18 over 2 or 27 over 3 and so on. And negative 5 can be represented as a negative 5 over 1 or negative 10 over 2 and so on. So, in writing rational numbers, whether they were initially integers or whole numbers, as long as the denominator is not 0, these are the rational numbers. Now, one of the things we often like to do is to simplify rational numbers to its lowest term. That is, take out factors of a number, such as if you originally had A times K over B times K, and since they're times, these are factors, here we have a common factor. We can cancel out K over K as a 1. A very useful tool. In example 1, we're going to write fractions in lowest terms. So we see something like this, 36 over 54. Well, they're both even, so we know we could take out a 2. Could we take out a 4? No. But interestingly, as they're showing down here, you could take out an 18. And if we wanted to look into this in more detail, we know that 36 is 4 times 9, and 54 is 6 times 9. But notice there's a 2 here as well. So this could be 2 times 2 times 9. And this could be 2 times 3 times 9. And now we see we have 2 sets of 1s, and 2 times 9 is the 18 that they're showing us here. So these would cancel out and make a 1. These would cancel out and make a 1. And you're left then as a simplified answer 2/3. And another little proof they're giving us as a tool that if we have then our original fraction simplified to 2/3, we can do what is called cross multiplication, where we can multiply this by this and this by this, where what is here and what is here is referred to as the extremes, that is the furthest away if you followed through, and then the 2 in the middle, this one and this one, are referred to as the means. This is the cross product check for doing that. And I could recall years ago saying the product of the extremes, the ones in blue, is equal to the product of the means. A little something. And here is the rule as the cross product test. for equality of rational numbers. So A and D are the extremes, B and C. Now, as we look at this operation with fractions, which is sort of a synonym for rational numbers, we see we have 1/3 plus 2/5 that we'd like to add. Now, we can't add these fractions because the values within them actually have different values. If we look down here for the representation of 1/3, we have one of these out of the 3. For the 2/5, we have 2 of these out of 5. And you can see what's in the blue as a 1 and what's in the red as a 1 does not have the same value. So the 1 part, 3/3 and 5/5, that has the same value, but the numerators do not. So when we are dealing with fractions, we must have what are called common denominators so that the numerators reflect a true value in terms of the other. So what do? Well, we have to have a common denominator. And to do this, to give you some background, we are allowed to multiply every number by 1 and not change its value. But the choice of our 1 is such that we're going to multiply this 1/3 by a 1 in a form that will make our denominator a 15, which between a 3 and a 5 would be our common denominator. So what do I need to multiply the 3 by to make it a 15? And the answer is 5. So the 1 here that we're going to choose is 5/5. And what form of the 1 will we choose here to make this a 15? And if you said a 3/3, that is correct. So again, we are authorized to multiply anything by 1. That's the identity of multiplication. So now our denominator becomes 15, our numerator is 5, and our 2/5 become a 6 in the numerator and a 15 in the denominator. So this then becomes an 11/15, and we see that by making the 3 parts here into 15 parts, making each one of these 5, our 1 values now are true 1 values in our modified fraction. I like the way they've set this up, an excellent way to show it. And in your textbook you see exactly what they are doing. So the rule then, as is described here, is that if you have fractions of different denominators, you must get the common denominator by multiplying each by the 1, that form of 1 that will make it into your new least common denominator. So let's do some practice. So the first thing here is to pick out a common denominator, and if you can see it, that's good. We'll show you a method here shortly, but 30 is our common denominator. Now, a shortened form of what we did before is, what do we need to multiply 15 to make it 30? And if you said 2, that's the form of 1. So 15 times 2 is 30. 2 times 2 then is 4. What do we have to multiply the 10 by? And again, it's a 1 in the form of 3 over 3. So we then get 7/30ths as our answer. Now, B is a little more complicated. In looking at B now, this is a little more complicated. Looking at this, I see an 18, and I see a 12 there, and I see a 36. But this is 1200, so I see 2 zeros there. Now, what do I need to multiply 180 by to make it 3600? And the answer is 20. So I'd have to multiply this by 20 over 20. This becomes 3600, and my numerator becomes 3460. And remember, there's a negative sign there. Now, this one's easy. What do I need to multiply 1200 to make it 3600? Well, a 3. A 3 over 3. Again, we're multiplying these by 1, but the ones can be any different form so that it makes our denominator our common denominator. And this now becomes 207, which when we do this subtraction, we get 3253 over 3600. So they jumped from a rather easy one to one that was very challenging. Now, some other background. Now, when the numerator of a fraction is larger than the denominator, we call this an improper fraction. And we can convert that to a whole number. 2 goes into 3 once, and there's a 1 left over as a remainder, and we get this. So this is an improper fraction, and this is what we call a mixed number. Now, if we have a mixed number, we can convert it to an improper fraction by saying our denominator over here at 2, 2 times 1 is 2, plus 1 is 3, over the 2. So we can work back and forth. So they're asking us to perform each conversion to take 2 5/8 as a mixed number and convert it. Well, we would go 8 times 2 is 16, plus 5 is 21, over 8. 8 times 2 is 16, plus 5, 21 over 8. They're making that one a little more complicated here. Now, for this one, we're going to divide 5 into 8, and that goes once. And then there's a 3 left over. 5 into 36 goes 7 times, and there's a 1 left over. So 5 times 17 is 85, plus 1 is 86 over 5. And again, these are the ways that I've learned it there may be other ways to do it. I think this is the easiest. Now, as we move into multiplication of fractions, the general rule is multiply your numerators, multiply your denominators. Now notice there are no common factors that we can cancel, and we should do that before we multiply. So let's look at some examples here. In letter A, are there any common factors? No. So we just multiply the 3 times 7 and get 21, and the 4 times 10 and get 40. Now, since we couldn't cancel anything out here, we can't cross-cancel or do anything there. But as we look at letter B, notice we can do some cross-canceling. And so as not to destroy our original, I've written it out again. Now I can take a 5 out of there, that goes once. A 5 out of there, that goes twice. I can take a 3 out of there, that goes once. A 3 out of there, and that goes 6 times. So now I've simplified my fractions, and for my numerator I get 1 times 1, and my denominator I get 12. Now had you done it the way they suggested, you would have ended up with a 15 over 180, and you would have to try to cancel out 15 out of there and 15 out of there. I think it's much easier to do it this way, so that when you end up with your answer, it is already simplified. And they're showing that down here as well. Now in example C, we have mixed numbers. So what you would do first is convert them into improper fractions. 3 times 2 is 6, so that is 7 over 3. 2 times 1 is 2, this is 3 over 2. Now notice you can cancel out the 3's, so your answer would then be 7 halves. And then to convert that to a mixed number, 2 goes into 7 3 times. There's a 1 left over. And you can always check your work. 2 times 3 is 6 plus 1, 7 halves. And that's what they have. Okay, now going into division, again, you can never divide by 0. But another way to look at A divided by B is to say that A times 1 over B. So we can convert this to a fraction. Now in division, they're going to give us some rules, and I will go over them. It's kind of detailed here, but let's look at this. Here's your basic rule for dividing fractions. If we have A over B divided by C over D, the general rule for dividing fractions, the first item, A over B, stays the same. We convert the division to multiplication, and now take the reciprocal, or flip the second item like so. So C over D, flipping it gives us D over C. So then we just carry on our multiplication. So anytime you have division of fractions, we will convert it to a multiplication by flipping, taking the reciprocal of the second item. Let's try some. And one of the things we might do also here, what will be our sign at the end of this? Well, it's going to be positive. What will be our sign here? Negative. Here, positive. Here, negative. Now, there's only one other little modification we need to do. This doesn't look like a fraction here, so let's just put it over 1. This doesn't look like a fraction, so let's put it over 1. Now, what we're going to do in each of these cases is change that division sign to multiplication and flip this. Multiplication, flip. Multiplication, flip. Multiplication, flip. And wherever we can simplify, we do that. So it's worked out nicely here. And to not have this run too long, you can just observe what's here. Keeping in mind, whenever you do one, in fact, let's just do this one. This is going to be a negative 9 over 1 times 5 over 3. Now again, negative, unlike signs, the answer will be a negative. The 3 will cancel there. And we now have a negative, these are 1s, 15. And that's what they have here. So again, we changed it to division to multiplication, flip the second. And we determine our signs by, if it's like signs, it's positive, unlike signs, negative, and we've gone through the steps. Now we're going to put all of our skills together as we have this carpenter who has a board that is 6 feet long, which is 72 inches. He must cut it into 10 pieces of equal length. This will require 9 cuts. Again, a diagram may help you. So cutting this into 9 pieces gives you the last one of 10. So now we have 10 pieces here. But each cut, because of the blade of the saw, will take out this much of our overall length. So how many inches of actual board will remain after the cuts? Well, we're going to have 9 cuts times this. So we will then say our overall length of the board is 72 inches. Each cut is 3/16, and there's going to be 9 of them. So minus 9 times 3/16. So when you do this multiplication, so they're modifying this to show the multiplication here. This will be a negative 9 times 3, a negative 27/16. So there's our negative 27/16. But again, this is over 1. So our common denominator will be 16. When we multiply 72 by 16, we get this. We now do our subtraction. We get this over 16. And then convert it back to a mixed number. So our original board that was 72 inches now becomes this. So what will our equal 10 pieces be? Well, we would have to divide it by 10. And again, we change it to multiplication by taking the reciprocal of 10, which is 1 over 10. And we can cross-cancel a little bit. Take out a 2, 5, and get a 2, and this, so that each piece will be this as an improper fraction, or this as a mixed number. And again, quite tedious and challenging. Now, as we go deeper into the theory of numbers here, we're looking at density and the arithmetic mean. Now, there are no integers between two consecutive integers, such as 3 and 4. These are integers, and there are no integers between them. However, there are rational numbers between them that are fractions. So, for this reason, the set of rational numbers is said to be dense. That's the density of the rational numbers between a 3 and a 4. Now here's the rule. If r is less than t, there exist between them rational numbers that make up set S, in a sense. So these would be on a number line. Oop, didn't do too well there. A 3 and a 4. All of the numbers, the rational numbers that exist between the two of them. Now, how many are there between each set? And the answer is there's an infinite number. Why? Because you keep going on and on and on and on, and it would never end. And I'll read this. One example of a rational number that is between two distinct rational numbers is the arithmetic mean. That's often referred to as the average. To find the arithmetic mean, or the average of n numbers, we add the numbers and then divide the sum by n. For two numbers, let's say 1 and 2 on a number line, the arithmetic mean would be right in the middle. So you would add the 1 and the 2, get a 3, and you're adding two numbers together, so your n is 2, so your mean is 1.5, or 3/2. Now, they're not going to give you an easy one like this, or maybe, but let's look at finding the arithmetic mean of these numbers here. So we have 1, 2, 3, 4, 5. We add them up, and we're going to divide by 5. That's how we find the arithmetic mean, or the average. Now, you did all of that, and you get this answer, which would end up as a decimal, which is 1/5, but they want you to round to the nearest dollar, so you would drop the 1/5. If it were 3/5, you would have added 1 to the 4. It would hurt me to see you did all of this and just messed up on the rounding. So be sure to follow those directions. Well, that was pretty straightforward. Now we're going to find measurements in a socket wrench set. And here we have sockets that are fractions. And we want to find the average between two fractions. And this describes it. So what does he do? Well, we have to add our fractions together and then divide by 2. So there's the sum of our fractions. We're dividing it by 2. How do we divide fractions? Well, we change from division to multiplication and take the reciprocal of this. So when we flip the 2 over, we get 1/2. And then now 7 times 1 is 7, and 8 times 2 is 16. So he must use the 7/16 inch socket. Okay. Decimal forms of rational numbers. We're going to take a look now at decimal forms. And I like the way they have this laid out. There's the decimal that we use in our mathematical system. And then the number 483 point, and then all of this. Well, what is the terminology to describe these various places? Well, the one to the left of the decimal, these are the ones, these are the tens, and these are the hundreds. And to the right, that decimal place is tenths, hundredths, thousandths, 10,000ths, 100,000ths, millionths with a THS after each one. Wow. Okay. Now, rational numbers in the form of A over B, which is our form of a fraction, can be expressed as a decimal most easily by entering it into the calculator. Put that into the calculator, hit equals, and you get this. So this decimal is this fraction. Now in the old days, before we had calculators, we would have to do it by long division, as is shown here, and you get the same answer. Now notice in this case it terminates. Again, why it's called a rational number. Now if you tried another, say 4/11ths, and you divide 11 into 4 in the old-fashioned way, you'd start to get 3/6, 3/6. You would get a repeating pattern. And they give you other examples here. Now the text is saying that what we do often when we find a repeating pattern, we put a bar over the part that repeats. This bar, called a vinculum, over the block of digits that repeat, such as this. I hadn't seen this word in a long time, but there it is. So we had said that fractions, when we put them in decimal form that terminate or repeat, are the rational numbers. Now, as looking again at the text, they say that some mathematicians considered all rational numbers as repeating decimals, where 3/4 would actually terminate at 5. Theoretically, you could write zeros after them, and the 0 would be repeating. All right, one way to think of it. Let's go on. Now, here they're giving us a general rule for decimal representation of rational numbers. We say any rational number can be expressed as either a terminating decimal or a repeating decimal. We know this. But how do you determine the fraction will be terminating or repeating? And they're saying if you look at what is in the denominator of a fraction, and if the prime factorization of that denominator has a 2 or a 5, because we are using the decimal system in our number base, we use base 10. So if these are the prime factorization, then it will terminate. But if it's numbers other than 2 and 5 as prime numbers in your factorization of the denominator, then it will result in a repeating decimal. So let's take a look at. So looking at our first example, 7/8, what is the prime factorization of 8? So we can do it like so. 2 goes into 8 4 times, 2, 2. So there's our prime factorization of 8. And it would be 2 to the 3rd. Well, since in our denominator the prime factorization are 2's, this has a terminating fraction. And you can read it here as well. Now as we do 150, we can take a 2 out of there, 75, we can take a 5 out of there, and that is 15. We can take a 3 out of there, and that is a 5. So our prime factorization contains 2 5's and a 3. Because it has a 3, not just a 2 and a 5 when we simplify it, this will be a rational number that repeats, again because of that 3. Now as we look at this one, we have 6 over 75, and we know we can take a 3 out of each one. 3 out of there is 2. 3 out of there is 25. Now the prime factorization of 25 is a 5 and a 5. Now, since the prime factorization of the denominator in its simplified way is 5, could also have 2's but doesn't, it has 5's, it indicates this will be a terminating fraction. Okay, and we see the answer there. All right, let's go on to example 10, writing decimals as quotients of integers. In our last example, we're going to write each decimal as a quotient of integers. So this is to the thousands, so we just put that over 1,000. And that one's pretty easy. For letter B, we put this over 10. This is to the tenths. And to get rid of our single decimal point there. In a sense, it's 8 2/10. So converting it to a improper fraction, 10 times 8 is 80 plus 2 is 82 over 10. And since we could simplify it a little bit by taking out a 2 out of each one of these, we end up with 41 over 5. Now in example C, this is the challenging one. So we'll use the text because I'm not going to write all this out. We're going to use a little algebra. We're going to say let x equal this. So in a sense, x equals this, and it's a repeating part. So multiply both sides of the equation by 100. That is 10 to the second. So we get x equals this. Multiply each side by 100. So we get this, and we'll go to the next page. This part is tricky. We're going to subtract now an x from this, or that first equation from this, and we now get 99x equals this. We then solve this equation by dividing both sides by 99. And we end up with x equals 85 over 99. That if we were to divide this, it would give us this repeating fraction. So this one's complicated, and you're able to use your textbook to just follow it as an example. Okay, this wraps up this part, and there are some exercises, and we will have hopefully some class time to do some. Okay, topic 3.6, lots of stuff here.